Hi students, in this class we are going to learn the capacitance of three-phase transmission lines. Consider these three conductors. If you look at the cross arms, this cross arm is longer than this cross arm. So these three conductors are unsymmetrically positioned. So the distance between these three conductors are different. Suppose the charge flowing through these conductors are Q1, Q2 and Q3, because you know the current is equal to charge divided by time. So each conductor is carrying a particular charge. And suppose the radius of each conductor is r meter. This is the radius of each conductor. Now we are going to find out the capacitance of each phase. So this is the formula we are going to use. Q is equal to CV. You can remember the name CV Raman. So first of all, we will find out the potential difference. With that potential difference, you can find out the capacitance. So this is what we are going to do in this problem. So first of all, we will find out the potential of the phase A. So the potential VAN is contributed by all the three charge carrying conductors. So VAN can be written as 1 by 2 pi epsilon 0 into the potential of the conductor A due to its own charge. Here the charge is Q1, it is R to infinity dx by x, plus what is the potential due to the second charge carrying conductor. Here the charge is Q2, that is Q2 divided by 2 pi epsilon 0. Here the distance is d1, that is d1 to infinity dx by x. Now what is the potential due to the third conductor? Here the charge is Q3 divided by 2 pi epsilon 0 into the distance is d3 to infinity dx by x. So we can factor out 1 by 2 pi epsilon 0 q1 into what is the integral of 1 by x? It is log x. So q1 into log x. The limits are from r to infinity, plus q2 into log x. The limits are from d1 to infinity, plus q3 log x. The limits from d3 to infinity. So this can be written as 1 by 2 pi epsilon 0 into q1 log infinity, upper limit minus lower limit, q1 log r plus q2 log infinity minus q2 log d1 plus q3 log infinity minus q3 log d3. This is equal to 1 by 2 pi epsilon 0 into This minus Q1 log R can be written as Q1 into log 1 by R. It is Q1 log 1 by R. So this can be written as Q2 log 1 by D1. Q2 log 1 by D1 plus this is Q3 log 1 by D3. Q3 log 1 by D3 plus this is Q1 log infinity, Q2 log infinity, then Q3 log infinity. So Q1 plus Q2 plus Q3 into log infinity. What is Q1 plus Q2 plus Q3? This is 0. Now Q1 plus Q2 plus Q3 is equal to 0. We assume that it is a balanced system. So I1 plus I2 plus I3 is equal to 0. One by 2 pi epsilon 0 into Q1. So this term is 0. Log 1 by R plus Q2 into log 1 by D1 plus Q3 into log 1 by D3. So this is the potential of the first phase. Similarly, we can find out the potential of the other two phases. VBN we can find out, and VCN also we can easily find out. Now if you calculate the capacitance, you get three capacitance: CAN, CBN and CCN. These three capacitance will be different. So the charging currents in the three phases will also be different. Charging currents will be different. Actually, we want to have the same charging current in all the three phases, or we want to have the same capacitance in all the three phases. How can we make the capacitances in all the three phases equal? By doing the transposition of conductors, the capacitances in the three phases can be made equal. It is just like what we studied in the inductance of conductors. So here the positions of the conductors are interchanged. This is the position of the three conductors in the first 1/3 length of transmission. Then you see the A phase is brought to this place. Then again after 1/3 length of transmission, the A phase conductor is brought to this place. So during the course of transmission, all the phases will be getting all the three positions, and thereby the potentials and the capacitance of all the three phases can be made equal. So the charging currents will be equal. So these are the three positions during the course of transmission. So if we consider one phase, here the potential of the phase A will be VAN1. During this position, the potential of the same phase is VAN2. During this position, it is VAN3. So the A phase conductor gets three potentials at the three different positions. So the average potential will be equal to VAN1 plus VAN2 plus VAN3 divided by 3. Because all the three phases will be having potentials, we can find out VB and VC. So in this case, if you are doing the transposition of conductors, the capacitances will be equal. So your CA will be same as CB, will be same as CC. That's why we are doing the transposition of conductors. So this is the potential of the phase A conductor at the first position. We have already written this expression. Now we can find out the potential of A phase conductor at the second position. Is 1 by 2 pi epsilon 0. Looking at the first expression, we can make the second one. There are only differences. D1 will be changed to D2 and D2 will be changed to D3. D3 becomes D1. One cyclic shift will be there. This Q1 log 1 by R plus Q2 log, the D1 becomes D2 plus Q3 into log D3 becomes D1. Similarly, what is VA-N3? Is the potential of the first phase at the third position. Is 1 by 2 pi epsilon 0 into Q1 log 1 by R plus Q2 log D2 becomes D3 plus Q2 log D1 becomes D2. So these are the three potentials at the three different positions. Now what is VA? The average potential of the A phase is equal to 1 by 3 VA-N1 plus VA-N2 plus VA-N3. So this is equal to 1 by 2 pi epsilon 0 into, this is equal to 1 by 2 pi epsilon 0 into, you see these three terms are equal. So you get 3Q1 log 1 by R. So that 3 and this 3 will be cancelled. That is Q1 log 1 by R plus, if we look at these three terms, Q2 into log 1 by D1, log 1 by D2 plus log 1 by D3. Combining these three terms, it becomes 1 by 3, or I can write Q2 by 3 into log 1 by D1, D2, D3, because log A plus log B plus log C is equal to log ABC, plus we look at these three terms, it is Q3 into log 1 by D1 plus log 1 by D2 plus log 1 by D3. So this can be written as Q3 by 3 into log 1 by D1, D2, D3. All logarithmic terms are with base E. So this is equal to 1 by 2 pi epsilon 0 into Q1 log 1 by R. If you look at these two terms, we can factor out log 1 by D1, D2, D3. 1 by 3 log 1 by D1, D2, D3 into Q2 plus Q3. What is Q2 plus Q3? It is minus Q1, because you know Q1 plus Q2 plus Q3 is equal to 0. So Q2 plus Q3 can be written as minus Q1. So it becomes 1 by 2 pi epsilon 0 into Q1 log 1 by R plus Q2 plus Q3 becomes minus Q1. So this is minus Q1 by 3 into log 1 by D1, D2, D3. Again we can factor out Q1. This Q1 divided by 2 pi epsilon 0 into log 1 by R. So this is minus log 1 by D. What is minus log 1 by D? It is log D plus 1 by 3 log D1, D2, D3. So this is equal to Q1 divided by 2 pi epsilon 0 into log 1 by R plus this is 1 by x log D. What is 1 by x log D? Log xth root of D. This is the formula we are going to use here. That is log, all logarithmic terms are with the base e, cube root of D1, D2, D3. This is equal to Q1 divided by 2 pi epsilon 0 into, now this is log A plus log B. So this can be written as log D1, D2, D3 by R. So this is our, now we can find out the capacitance CAN. You have to use the formula Q is equal to CV. So C is equal to Q by V. Q divided by VAN. So this is equal to 2 pi epsilon 0 divided by log cube root of D1, D2, D3 divided by R. This is the capacitance of A phase. Its unit is farad per meter because we considered 1 meter length of transmission wire. Suppose they are symmetrically spaced, that is D1 equals D2 equals D3, D1 equals D2 equals D3, that is the conductors are symmetrically spaced. Now the CAN is equal to 2 pi epsilon 0 divided by log cube root of D cube by R. And this will be equal to 2 pi epsilon 0 divided by log D by R. So this is the capacitance of phase A if the conductors are symmetrically spaced, 2 pi epsilon 0 divided by log D by R. If they are asymmetrically spaced, then this is the capacitance, 2 pi epsilon 0 divided by log cube root of D1, D2, D3 divided by R.